Welcome back. I hope you enjoyed your lessons in Bayesian inference. I'm Zach Pitko, and now we're going to talk about some advanced Bayesian methods and new applications of the ideas that you just learned about. So first of all, who am I talking to you? I'm a theorist. I like art and music, especially sculpture. My favorite flavor is cherry, seconded only by mango. And I really don't understand this thing about coffee. Where does the name come from? Well, I invented that myself in high school and just liked it so much I kept it. It's kind of fun. Okay, let's get to it. This is what we'll be talking about in this lesson. First, I'll summarize your tutorials that you experienced so far today. And then I'll talk about how we can scale up, going to more complicated problems with many variables and more interesting, sophisticated applications. I'll talk a bit about shortcomings of these normative probabilistic models that we've been addressing so far. In particular, the idea that they do not have a mechanism. That leads us then to thinking about Bayes in the brain. Are there models? Is there evidence? Let's get started. First, let's summarize what we've learned. We covered the basics of Bayesian inference, in particular, the product rule and the sum rule. The product rule we used to understand Q combination, how you can combine different forms of evidence about the same underlying variable. And the sum rule, which taught us how to ignore or marginalize some variable that was not directly relevant to the task. When we were making decisions, we had to weigh those probabilities according to their utility, and that helped us shape our decisions and actions. And we implemented all of this thinking about Gaussian problems. So let's review. The product rule. So we had a prior, P of x, which was the probability of a target before we make any kind of measurement. And then we had a likelihood, which was the probability of the measurement given that target. We could combine these two by multiplying the probabilities to obtain a posterior, which is the probability of the target after you've made the measurement. We looked at this in Gaussians, and we found that when we multiply two Gaussians, the result is a third Gaussian. So we'd have a Gaussian posterior. And we can express the mean and variance of that posterior Gaussian in terms of the mean and variances of the prior and the likelihood. The variances actually added as a harmonic sum. That is, the inverse variance of the posterior was equal to the inverse variance of the prior plus the inverse variance of the likelihood. And that can be understood in the context of information, that the inverse variance is really a measure of information related to the Fisher information. So the narrower your posterior is, that is, the smaller sigma, the more information you have. And those inverse variances were actually the weightings for the means as well. We found that the posterior mean was a weighted combination of the prior mean and the likelihood mean, where you gave more weight to the more informative source. We also studied the sum rule, which allowed us to calculate the integral or marginal of a joint distribution to ignore one of the variables. This is something we used in Bayes' rule as the denominator. We figured out the probability of the data marginalized over all of the latents that could have generated the data. So here we have P of y is the integral of the prior times the likelihood, integrating over x. We also express this in terms of Gaussians. In particular, if we take the simple assumption that y is just a corrupted version of x, then we can express this, the resultant Gaussian P of y, especially simply because the variances add. In the product rule, the inverse variances add, but here the variances add. The uncertainties grow when you're marginalizing. And likewise, the means just add. We also considered Bayesian decision theory, where you would have a value associated with different answers of a choice that you would make or an estimate that you would take. We would establish a cost function there, saying, if the true answer was X, but you chose C, how bad was that? So here we have a cost function that is the absolute error. Now we can multiply that cost function by the probability of getting that answer, given the observations y, multiplying by the posterior. And then we get a weighted cost associated with each choice and possibility of x. And if we integrate those over x, because we don't know what the real x was, we can get an expected cost for each possible choice. If we minimize that, we get the best possible choice, the lowest cost, and that's the best single answer that we could get, given this cost function. Now we've learned a lot about Bayes' theorem, and so hopefully we'll be able to simplify this modified Bayes' theorem presented by XKCD, which shows this formula, including an interesting factor here, the probability that you're using Bayesian statistics correctly. You can see if that goes to 1, then you're going to get the right answer. Hopefully we've increased the probability that you're using Bayesian statistics correctly from these tutorials. Now, going from Gaussians of 1 or 2 variables to larger problems can be quite challenging. So we have to think about how to scale up our ability to think about probabilistic reasoning. We can see the problem even in simple cases where we have binary variables. When we have a lot of variables, there's really no hope to represent arbitrary probabilities. And we can see that by taking n binary variables, which therefore have 2 to the n possible states. Even if we have just a 20 by 20 binary image, this is over a Google possibilities. We need simplifications. How can we simplify? Well, if we're considering all possible images, we can exclude images like this one, which is just not typical and not interesting. What if we just enumerate only plausible states, only plausible images? Is that possible? Is that a workable way of simplifying the space of probabilities? What might be the problem with this solution? Think about that for a few seconds. The problem is there are far too many possible images in the world, even if you simplify to only natural ones. We need more. Conveniently, the world is structured, and there's a mathematical formalism that allows us to handle this kind of structure. It's called probabilistic graphical models. Not all variables of interest in the world directly interact with all other variables. We can describe a joint distribution by a product only of those direct interactions. So for instance, we might have a probability over x, y, and z, and we can write that, potentially, as p of x times p of y given x times p of z given y. These interactions form a graph. Nodes are variables, and edges are interactions or dependencies. So in this case, z depends on y, and y depends on x. Now, we can always write some kind of factorization using a probability chain rule, a product of conditional probabilities. But the problem is that the last node in the chain has to depend in general on all of the previous variables. And so that does not simplify the problem at all. The simplification comes when you eliminate some of these arrows, eliminating these dependencies. You say goodbye to the red arrows, and now we have a simpler probability, which has more structure. And as things get more complicated, that structure becomes more and more beneficial. The resultant graphical models can be simple, like a chain. This one here is called a Markov chain, where you might have something unfolding, for example, in time, or they can be more complex, like here this one showing a Bayes net which has no cycles, no loops where the arrows come back and meet head to tail. This is called a directed acyclic graph. Or your probabilistic graphical models can be very complex. This is just scratching the surface. The one on the right is a medical probabilistic graphical model used as an expert system to find out what disease might you have given a bunch of symptoms. Now those probabilistic graphical models have two different types of nodes. You can have an observation of a node, in which case we color it gray, and it would be given in a conditional probability. or latent or unobserved when we color it white. So then we can write down a probability, still structured, of the latent variables given the observed ones, p of x2, x3, and x4, given x1 and x5. And this would still be structured according to the graph that you see here. These probabilistic graphical models could represent many different types of variables and their relationships. They could represent space, they could represent time, they could represent pixels in an image, or stresses in a bridge, neurons over time, notes in music. In all of those cases, we have a rich tool set for manipulating these probabilities to draw inferences about things that are unknown. And all of that is founded on the lessons that you learned today. Next, we're going to turn to applications of Bayesian inference. We'll use those graphical models that we just talked about to think about large-scale brain networks and models of how an animal would act in the world using the perception-action loop. One common thing in brain imaging studies is the notion of functional connectivity, which really just means correlation. But it's helpful conceptually and scientifically to think about directed interactions, i.e., graphical models. This is usually done by estimating a big multivariate Gaussian graphical model. Not always, but that's a convenient way to do it. And just as you learned in your lesson, now we would fit the covariance instead of fitting a variance. Otherwise, the basic ideas are the same in their core form. Probabilistic graphical models allow us to think about direct interactions and distinguish them from indirect ones. So here, X and Z are not directly interacting, although they're indirectly interacting through Y. And that indirect interaction correlates them. So X and Z would be correlated even though they're not directly talking to each other. You can imagine that quantifying the direct interactions would be a useful way of measuring and quantifying the information flow between different parts of the brain. Another interesting application is the perception-action loop, whereby animals interact with the world based on their beliefs about the world. The brain has an internal model which helps the animal to interpret ambiguous sensory data, and then the animal chooses what actions to take based on those beliefs. The world state gets influenced by those actions, which then give more observations and hopefully some reward back to the animal. Those observations and rewards go back and update the beliefs, which are influenced by that internal model. And those beliefs have been associated with values which allow the animal to choose which is the best action. We can describe this as a probabilistic graphical model where all of those concepts have their own variable. You have some world states, you have some observations and actions, beliefs about the world, and rewards. And all of them are connected with each other over time. In order to understand this, we really need to think about time series and how that interacts with probabilistic reasoning. And that's what we're going to cover later in the week. Tomorrow and Wednesday, we'll cover models for time series and on including integrating observations over time about unknown latent variables. And then on Thursday and Friday, we'll use those tools to go beyond perception to include actions. The Bayesian approach is very powerful, but there are some questions that we have to address when we use it. For starters, where does the prior come from? It comes before we get any evidence. And so this is something that would presumably be inherited from evolution and development, and potentially informed by previous experience. But that previous experience is ambiguous as well, and so the learning itself comes with some prior on what should you learn from what you've seen. That prior itself is formed by, again, evolution and development, and the structure of the brain's computations and circuitry through the architecture, the nonlinearities, and the plasticity rule. All of those form an inductive bias, which forms a prior for what is learned. It's a learning prior, a learning bias. Even if you knew the right model for the world, one major problem is that exact inference is intractable. You just cannot compute the things you would like in realistic problems. So you have to use approximations. And which approximations do you use if you're a brain? That's something that the Bayesian approach by itself cannot tell us. It's something that we have to add to the approach. Similarly, we may be constrained in the computations that we can do, or not trying to perform absolutely every inference, but inference conditioned on some limitations like your metabolism. How many spikes can you produce? What type of sensors do you inherit? What subjective preferences do you come built in with? And what suboptimal computations are you restricted to based on your architectures? And ultimately, Bayesian approaches cannot answer how questions when we apply them as a normative model for what computation should be. It tells us why a computation should be done, but it doesn't tell us how. It doesn't tell us the mechanism. It doesn't tell us the algorithm or steps to take to reach that computation. Ultimately, it has no theory of computation. That has to be added to Bayesian inference. And that leads us very naturally to asking questions of how could the brain do it? Because that would require an implementation or a mechanism. So next I'm going to talk about a couple of models of how the Bayesian brain might be implemented. First of all, this is predicated on the idea that behavior is Bayesian, and there's a lot of support for that as we described in the introduction to the day. So if behavior is Bayesian, then the brain must implement those computations somehow. And recall again, normative models cannot explain how or where those computations are implemented, just why. So we need another hypothesis, linking hypotheses, to connect that Bayesian behavior to the brain. We'll talk about two different representations of uncertainty, temporal codes and spatial codes, following the idea of Savin and Deneuve. An example of a temporal code is the idea of temporal sampling. This idea is that one neuron represents one feature, and at every time point, those neurons offer their features as possible interpretations of the world. Then, as you go to the next time point, the neural activity may change, and therefore the interpretation would change. Over time, those neurons trace out a probability distribution, which therefore equals the joint feature probability in the world. So the neural probabilities equal the world probabilities. This is a direct representation of probabilities. So here we have a picture of a tiger on the left, and at 3 different times you might have different neurons active that encode the eyebrow slash there at different places, times 1, 2, and 3. So overall, you're not sure exactly where the animal's eyebrow might be, and you get a probability of distribution over that using those neurons. An alternative, which uses a spatial code, is probabilistic population codes. Here, you take an instantaneous projection of the neural activity at one time, and that encodes a whole posterior, or parameters of the posterior. Generally speaking, more spikes then equal more confidence. The red example here has more spikes, and it has a taller and narrower posterior over here on the right. The blue example has fewer spikes. Let's say maybe it's a lower contrast image, and so you're less sure about exactly what's being shown. Your posterior is shorter and wider. It's unclear which representation the brain uses, and people are very interested in finding evidence for those representations. But representation doesn't matter if you don't use it. We might find experimentally that a representation is observed in the brain, but that information might be thrown away. So in order to understand that the representation matters, the models must also explain computation. A crucial point about this is that no representation could be performing Bayesian inference with simple linear computations, just weighted averages, if you're going to do all of the operations you need for Bayesian inference, in particular the product rule and the sum rule. Let's say we had neurons that represented probabilities directly. Then we could do the sum rule very easily with linear computation, because the sum rule just adds up probabilities and therefore would just add up some neurons. But on the other hand, then the product rule which multiplies probabilities, would be nonlinear and therefore more difficult for the brain to accomplish. Conversely, you might say, oh, well, I know how to do products. I can just take the log, and then all I have to do to take the product of probabilities is add the log probabilities. Good. But then the sum rule is nonlinear. So you're going to need to do some nonlinear computation somewhere. And that nonlinearity has to be related to the question of representation in the brain, how those probabilities are represented. Again, this is a hot topic. So what evidence do we have for Bayesian computation in the brain? Well, one example goes back to look at the neural substrate of Q combination that we've seen many times psychophysically in the behavior. In particular, Bayesian inference predicts that sensory evidence about latent variables should be weighted according to their reliability, with the more reliable evidence given a heavier weight. And we saw the equation for that earlier. Fetch et al. Looked at this problem for monkeys trying to discriminate between different headings, using two different sensory cues. One is vision, and the other is their balance or vestibular sense, using linear acceleration. The monkeys were actually placed on a platform and pushed around in space, and they would feel that acceleration, and that makes you feel which heading, which direction you're going. The visual information came from optic flow patterns that they would see, like this, sort of like Star Wars. And you can change the reliability of these cues by changing the number of dots that are all moving in a coherent or consistent direction. What they find is that as you manipulate the reliability of vision, you change behaviorally how much weight the animal puts on that vision and versus the vestibular. When the vision is less reliable, it gives more weight to the vestibular cues and vice versa. So the monkeys do reliability weighting of their information. But this study also showed that individual neurons in the medial superior temporal lobe, which is responsive to self-motion cues, also weighted their cues according to the reliability. The neurons responded more to the visual cues when the visual cues were more reliable, and more to the vestibular cues when the vestibular cues were more reliable. So you can see this correlation here between the optimal weight ratio that you would expect to see from Bayesian inference and the actual weight ratio that the animals and in this case, the neurons actually afforded to those different sensory pieces of information. A study by Cao et al. Also looked at causal inference in the brain, which was another example that you studied in your lessons. And they found, using a similar kind of Q combination task as we talked about with the ventriloquism example, that activity in different parts of the brain seemed to be consistent, correlated with different aspects of the Bayesian computations that are needed to find whether there's one or two sources. So some areas of the brain were responsive specifically to the auditory information. No surprise, those are the auditory areas. Some areas of the brain were more sensitive to visual information. Then there were some other areas, getting deeper into the cortical hierarchy, that were sensitive to the fusion of those two forms of sensory evidence. And interestingly, in the frontal lobes, they found correlations with causal inference. The signals, the activity in those parts of the brain were more explained by causal inference than by any of those other types of signals. So this is answering questions of where in the brain might different computations be carried out. And then we can look in more detail at how those are carried out by finer scale measurements. To conclude, let's just think about a couple of viewpoints on how Bayesian inference can be used. One very common approach is to use it as a fitting tool, a way of interpreting and fitting models to data. This is the domain of statistical neuroscience, but it also holds for particle physics and economics and many different disciplines. Here we propose this as a good model for brain computation, and we can think of that at three different levels. At the task level or computational level, we know that Bayes is the best way to solve things. So this is what the brain should do if it's going to be optimal. Then that leads us to a hypothesis that the brain is optimal, that behavior actually does follow Bayes' rule. That's a testable hypothesis. And then finally, we have the implementation level, which says that if behavior is in fact following Bayes' rule, then the brain has to implement that. And so that gives us constraints on the computations. These are all things that are active topics of study. The task, we think about Bayes computation for machine learning, for example, or robotics. How can you actually perform these tasks well? Behavior, you can think about this for cognitive science. You might want to try to find good descriptions of behavior in terms of complex problems that you'd like to solve and relate to Bayes' rule. And finally, neuroscience, where we're looking for evidence that the brain is implementing Bayesian algorithms. And so these are all hot topics that maybe you want to touch upon in your research projects. So with that, I'm going to conclude this, this lecture on advanced Bayes.